Hello everyone, welcome to our new series. In this series, we are going to take some simulation example and we'll try to validate with the available analytical solution for those problems. So this is our first video in that series. So in this case, we are going to take an example in which an elastic panel A fits into a rigid socket B of height h. We are going to assume some Young modulus value of the E as a generic value, and Poisson's ratio is something that is greater than 0. So the objective of this simulation will be we are trying to predict the stress that is going to get developed in the x direction and the value of the displacement at the top edge are for a constant pressure P. So let's start first with the analytical derivation to see how the stresses are going to build and what is the analytical deformation value that we are going to get for this model. So let's first try to draw a free body diagram. So if I'm going to draw a free body diagram for this block, it's going to look something like this. So on top, there is going to be some pressure, and bottom, because this we are taking this as a x and y direction. So there is going to be some stress. So let's call sigma y, and in this direction again, because this body we are compressing in y direction, so it will try to expand in x direction. So we can put the stresses as a sigma x in this direction. So from this we can get at least one thing, one data, that sigma y is equal to minus p. So let's write it down as the first equation. Now if we are going to put the Hooke's law, so from the Hooke's law we will get E strain in x direction is equal to sigma x minus, this is Poisson's ratio, sigma y. Let's put it as a 2, and E into strain in y direction is equal to sigma y minus V sigma x. Let's give this equation as a third number. Now if we are going to put the values of whatever the values of, like as we got from this free body diagram, that is sigma y is going to be equal to the pressure that we are applying. So it will become E zeta x is equal to sigma x minus plus Vp, and this will become your E strain in y is equal to minus P minus V sigma x. Okay, so let's give it a number 4 and 5. Now if we are going to go through the problem statement once, what it says is that this panel A is actually going to be fitted in a panel B, which is a rigid socket. It means that whatever the strain that you're going to get developed in x direction is 0. So now if we are going to put the values in the strain is equal to 0, then we are going to get sigma x is equal to minus mu p. And now again, if we are going to re-put it in this equation, so we are going to get a strain in y direction is equal to minus p 1 minus nu square divided by e. So this is going to be my sixth equation. Now at this point, if we are going to integrate, because we know that strain in y direction is nothing my dv by dy. So if I'm going to integrate it, then I am going to get the displacement in y direction as a displacement in y direction as a function of some y values. So let's first of all, let's at this point, because we wanted to predict the sigma x, so let's write out the sigma x values. So we have got the first equation, that was sigma x is equal to minus Poisson's ratio into the pressure value. Now if we are going to integrate that, that is integration of dv is equal to, because the pressure is constant, so we can put it outside of the integration, and 1 minus Poisson's square divided by e integration dy. So if v at y is equal to minus p 1 minus nu square divided by e into y plus constant. Now again, if we are going to go back to the problem statement, we can see that this region, like at y is equal to 0, whatever the material points are there, they cannot move in the y direction. So if we are going to put that thing, so 0 is equal to minus p, and y is also 0. So I'm just putting some like y is equal to 0, so we can directly multiply and it will become 0 plus c. So it will become your constant is equal to 0. So now if I'm going to put, my equation is going to be like this: vy is equal to minus p 1 minus Poisson's squared divided by e into y. So this is my seventh equation. So we got two values. One is your sigma x should be equal to minus Poisson's ratio into the pressure that we are applying. So let me put this diagram again. So this is my pressure that we are trying to apply. So whatever the stress that we are expecting in this direction should be equal to this value. Now the another thing is that if, because we have started a coordinate system y from the location, from the bottom location, so definitely at this location at y is equal to height h, if I'm going to put it, so it will become minus p 1 minus mu square divided by e into h. So that is my final value. Okay, so this is my y at h location. So now let's see that from simulation how closely we are able to match this results. I have already created a geometry, but what I will do is that I will explain the critical things that you need to keep in mind while modeling any plane stress type of phenomena in ANSYS mechanical. So first of all, whenever you are creating the geometry, either through the standalone component system, or suppose if you are adding any static structure, then this option will be embedded inside the component system of the static structure. So first thing is that whenever you are starting with the geometrical modeling part, before even opening the space claim or design modeler, go to this option and change this to 2D. So if you don't change it to 2D, so what will happen is that once you try to reopen the model in the mechanical, it will start throwing out the error message. Now the next thing is that I will open the geometrical part and then I will show you like what is the next part that we need to actually consider. So the next thing is that whatever the geometry that you are going to create must lie in the xy plane. So if the geometry is offset and it doesn't completely lie in the xy plane, again you will start getting some error message. So here you can see I have created two bodies. So one body is like something that is representing the socket, and another is that this is the plane where we are actually trying to deform the body. So it is deformable body, this is rigid body. So I hope this part is clear, like whenever you are starting with the plane stress modeling part, how to create the geometry for that plane stress modeling. So let me close this one. And now, as we want to perform this static analysis, because we are not interested in seeing the dynamic response that might get developed due to the application of the pressure, because was no data that was given in that problem statement, like in how much time that pressure was getting applied. So I assume that the author is assuming the pressure is something that is getting applied in a long duration of time. So that is something that means I will discuss like how to decide the this which time or which analysis system to take. Even I have briefly covered those things in one of our last video, so I will put the link of that video in description. So let me add this one. So now as I already have the geometry, so I'm going to transfer the geometry directly to the static structural component system. The next thing is that I'm going to take the static structural steel, because as we discussed in the problem statement, whatever the stress or the deformations value that we are going to get will be something that we can easily able to derive based upon the young modulus and the Poisson's ratio that we are inputting here. So it's any value we can put here. Only thing is that we need to re-verify with the equation that we achieved after solving that, like all the plane stress formulations and the Hooke's laws that we went through in the last last minutes. So let me open this one. So once we open the model in the mechanical, so the first thing is that let me once go through the problem statement. So this was the problem statement. The socket B is considered to be the rigid and socket A is flexible. So let's first see how we can actually define the different stiffness behavior for different parts that we imported in the mechanical. So if you go to the geometry tab and again click on any of this geometry, parts, then you can see that here we have an option to control between different type of behavior for that specific part, like flexible, rigid body beam. So these are something that is applicable available once you activate the beta features. So for this case, let's first confirm that the assumption that we are using is plane stress, not any plane strain or axisymmetric type of formulation. So if I'm going to click on this geometry tab, I can see the 2D behavior that we are using for this problem is plane stress behavior. Okay, so one thing is confirmed that we are going with the plane stress assumption. Now the next thing is that you can check the thickness values. So here we can see the thickness values are something that is getting used in the metric system, like 1 meter. But if I am going to compare this values, like if I'm going to check this thing and change this unit system again back to mm, so I can see the length is 37 mm. So it doesn't make sense that I'm going to use a 1 meter thickness for any plane stress type of model. So if it's 37, so let's take a rough value of 0.1. Okay. So now this is something that definitely the thickness is something that is very small compared to any in plane dimension of the model. Okay. Now the next thing is that if I'm going to click here, I can go to this stiffness behavior. I can change it to rigid. Okay. Now I will show you one thing, like whenever we are going to change this body to rigid behavior, what actually happens. So now this is going to be the flexible. So only thing is that I have to change the thickness to the same value that I'm using here. So we cannot use different thickness values for the different cases. Only thing is that some loads will get transferred differently. But yeah, means that is not something that means I will discuss those things in one of our upcoming videos, like how this thickness affects the plane stress behavior. But let's for this problem, let's focus on the our main objective, that is stress and the deformation at this specific location. Now the next thing is that I can go here and I can see that by default it has created some contacts. So I can see there is some question mark that is happening here. So usually if your target is flexible and contact is rigid, then you will get this type of error message. So just to get away with that error message, I can flip the contact and target. So that will work. But as per the problem statement, we need to define multiple contacts, because in this region your contacts are going to behave in a bonded behavior, and in this region is going to behave in a frictionless manner. So let's change the definition. So for that, let me first hide this body, because we need to define some different bond edge selections. So as this is going to be on my rigid side, so what I can do is that I can put it as a target. So so that this selection will be like, because the solver will understand that this is going to behave in a very rigid manner. Now I will invert the visibility and let me select this one. Now let me show all bodies and create another. So insert, I will create one manual contact. So before even selecting the contact and target, I will change this behavior to frictionless behavior, and the rest all the settings we can leave it as a default settings. Let me hide this one and select these two edges on contact side, invert visibility, these two edges, the target side. Okay. Now notice one thing is that what is happening when I'm going to create some mesh. Let me create quickly the mesh. So you can see that wherever we have defined the contact, some contact elements or the target elements are getting created. But for the rigid body, there is no specified element that gets created. And as we understand from a theory of finite element method, if we are somehow able to reduce the total number of elements in a model, it means that we are saving some computational time. So just keep in mind, like whenever we are using a rigid body formulation, it means that we are trying to save some computational time for a means at a solver level. Now let's look at this one. This is my rigid, this one. So for this body, there is no mess. And just to make sure that suppose in case if you are wondering that. So these were something that got defined as a target. Let me show you. So these were the target site. So here, if we look at the mesh, so the mesh elements are still getting created. So wherever the contact is present, the mesh will internally get created for you. So now the next thing is that let's me go back and we have to fix this body. So I can go, and whenever you want to define any displacement boundary condition for rigid body, then you have to use remote displacement. So for this, I can select this full face, remote displacement. I can give 0, 0, 0. And here you can change the behavior to rigid. Now the next thing is that I will go back and let me invert sorry, not invert visibility, pressure. So let me apply a pressure of let me just apply a 1 MPa, not more than that. Means you can definitely try with the other values, but let's for a timing, because we are trying to compare with the analytical expression, and I don't, because though that analytical expression is completely based upon our linear assumption, so I don't want to go into the non-linear regime. So that might be, that's the reason I'm trying to apply some values which can be easily correlated with the experiment, means analytical expression that we have. Now here you can see auto time stepping set to program control. So what I will do is that, just to get some data points, what is happening during the solution, I will set the value 10, 10, 10. So I will explain what is actually going to happen when you are going to set initial substep, minimum substep, and maximum substep. So if I go back here, pressure. So I'm applying 1 MPa of the pressure over this model. So whenever I'm forcing the solver to take some minimum substeps of 10, it means that I'm telling the solver split whatever the load that I'm applying into 10 parts. So it means that for each substep, the solver can maximum the load that can be applied to from the solver's perspective is going to be my 0.1 MPa, not more than that. So definitely for a very non-linear type of problems, we need to play around with these values, because that becomes very critical in order to get a good converge solution. Now let me solve this one. Okay. Okay. What it is saying? Okay. Solving. Okay. So let me plot the total deformation. And so once I add the total deformation, I can also see the vector view. So that is one very good feature, just to get an idea how the flexible body is deforming. So now if I'm going to activate, I can see that due to the pressure, the maximum deformation is something that is going to happen in this range. Now to get a better feel that how the deformations are varying along the y length, I can go deformation and let me put a directional for this time. So I'm interested in y directional deformation, and let me hide this body, because this is a rigid body and no deformation is going to take place for this body. So I will select this edge and evaluate all results, and then I can click convert to path results. Now you can see this is some type of linear deformation that is happening from minimum to maximum for this body. Okay, so only thing is that, okay, so it's showing 1 to 2, so it's starting from top to bottom. That's the reason it is showing like that. Otherwise you will see the red region actually represents a very low value that is near to 0. Now the next part is that we need to compare the stress in the x direction. So that was mu into p. So whatever, let's first check what is the Poisson's ratio for structural steel that we have entered. So it is 0.3, and if I'm going to multiply with 1 MPa, so it is going to become 0.3 MPa. Oh, let's go stress, and I will, in this case, I will use the normal stress. There are definitely multiple options. Like you can plot the equivalent, maximum principal, middle principal, principal. So you can go through all these features. But let's, for this case, I'm interested in the stress in x direction. So I will go here and I will plot this stresses. Oh, now you can see the values are something that are close to 0.24325. Now the values are very close to whatever we have got from the analytical expression. So it's 0.24 MPa. Now, as we are getting some different behavior, like one thing is that the stress that we are expecting is something that is going to to be constant. Now, suppose if I go back here, because we are something in an analytical problem, only constraining the motion of these material points in the y direction, but still these elements were free to move in x directions. So if we are going to change the behavior of that bonded contact to frictionless, we will be able to get a constant stress for this specific case. So if so, the values are actually much little bit more improved. So we were expecting zero point 0.3, but we are getting 0.26. Now there are ways using which we can actually further improve these results, but for a time being, it's because if you look from the error point of view, usually if some error is less than 10%, so that is something that we can accept from the problem statement, because now you can see this whatever the analytically plane stress assumption that we are using, it's completely like assuming that whatever the thickness is very very small compared to the in plane direction, so there might be some difference. So it's better like you can like compare this one, zero point 0.3. Let me just see how much difference is. So there was actually around 13% of the error, but yeah, definitely we can make this problem because we already have some analytical expression. So suppose at that point, if we have seen that because we are now using contacts which are actually penetration based contact. So if we go in little bit detail, so it means that there are some springs that are connected between contact and target nodes, and there is definitely going to be some penetration. Now let's see that if we are avoiding any penetration between contact target, and how much stress that we are able to generate in that specific model. So for that case, what I did is that I changed the behavior to normal Lagrange and resolved the model. And now in this case, if I'm going to check the stresses, I can see that whatever the maximum value that I'm going getting at this location is around zero point 0.3, and that is exactly matching with my analytical results. Now, if we are going to compare the deformation value, that the maximum deformation what we are expecting with the analytical expression. So let me just see this deformation body and plot the y-axis. Okay, so it is around. Okay, let me change this value unit system just to get a better feel. So because these displacements are very very small, so it's around 0.1547 micron. Now, if we want to compute or correlate it with whatever the values that we are getting from this one. So let me just use this scripting feature because it's a Python based, and we will be able to easily do some simple expression or the mathematical, not means you will be able to actually use all the Python codes here, but I'm using it for simple mathematical calculation. So V is equal to zero point 0.3. Pressure was 1 MPa. So I'm going to put 1 e to the power 6. Okay, something I did wrong. E is equal to 1 e to the power 6. E is equal to, I think that let's check the accurate values we are using, because let me first change it to MPa. And okay, right, okay, this is not getting a scale. So it's around 200 gigapascal. So, so 2 e to the power 11. 2 e to the power 11. Now, if we put the expression, whatever we got for the displacement at height h, so let's also measure the height h. So I'm using everything. So it is around 3.4 e to the power minus 2. So that is going to be my height. 3.4. What happened? Okay. 3.4 e to the power minus 2. Now let's write out the equation that is for V1. I will call that displacement at our height h is equal to V1. So V1 is equal to 1 minus v star star 2 divided by e. Let me put another bracket into h. Oh, got it. So I actually forgot to multiply the pressure here. Okay, so let's call it as a V2, and V2 is equal to V1 into P. Okay, so I think this value should match closely. So it's around 1.54 e to the power minus, and it's exactly matching with the values that we are getting at this point. So if we look at this problem statement and whatever we are expecting through the analytical expression, it's closely matching. Like, definitely if you go with some mathematical simplifications like penalty method and other things, then definitely the analytical expression will closely match it. So one thumb rule is that usually if something is within the 10% limit, so it's something that can be acceptable. But suppose if you want to further match your results closely with any of this analytical expression, so definitely we have to see what are the simulation assumptions that we are using, and then if required we have to relax those assumptions in order to move more closely towards the actual scenario. So that's all I wanted to show in this video. Thank you, and let's in next video I will take another simulation example, and definitely in the same fashion we will discuss first derive the analytical expressions or the analytical results, and then go towards the simulation, so that you will get more familiarized like how to uh, revalidate your model. So just to re-emphasize on the fact what we actually learned through this video, one is that how to use the rigid body in the model, then how to use plane stress models, and then in that case suppose if contact sensitivity is there, so how we can avoid those contact sensitivity for that specific case. So thank you, let's see you in the next video.